Good morning, everybody, and welcome to our third and final day of the symposium. So we hope you've been enjoying it so far. And today, I'm pleased to say we have a full program of parallel sessions, and we also have two excellent keynote speakers as well. One thing I would just like to say is after our second keynote speaker, which will be in the afternoon, we will go straight on into the closing ceremony. And could I please encourage you to stay, because this will be an opportunity to congratulate the winners of the Student Awards. I think there may be some other awards as well. And also there will be a presentation on the 43rd Symposium, which of course is next year in Charlottesville, Virginia. So please do stay for that. I'm now going to hand over to Esther, who's going to introduce our keynote speaker. Thank you, Esther.
Okay, so welcome again, everyone, and thank you very much for being here today with us in the Arnold Zellner Memorial Keynote Address. It's a real honor for me to be the chair of this session, and it's also an honor because I am going to introduce my friend and colleague, Massimiliano Marcellino. If I want to introduce him properly, I will spend too long time. So as the important thing today is to hear what he has to tell us, I am going to be very brief. So Massimiliano is now full professor of econometrics at the Department of Economics in Bocconi University. He is research fellow at the Center for Economic Policy Research and at the Innocenzo Gaspanini Institute for Economic Research. He has been visiting fellow at University of California, San Diego, and Harvard University, and research fellow at the European University Institute, among many other positions. His main research, if I had to define what is the area of his research, could be just called in general time series econometrics. I know that this is too broad, there are too many things there. And the main focus could be macroeconomics, although he also has many methodological contributions. Among these contributions, he has very important seminal papers in nowcasting, mixed frequency data, Markov switching models, Bayesian vector autoregressive models, forecast evaluation, business cycle modeling, and, well, I can just keep going with many other important topics with seminal papers. I insist that one of the amazing things about Massimiliano is that many of his papers are very well cited. And just to show you the relevance of his work for both academics and policymakers, I am going to point just a couple of papers because he's also one of the favorite authors in the International Journal of Econometrics. He has many contributions to the journals. Of course, you know that I am one of the editors of the journal, and I have to just point out that he has published important works. For example, one about the Midas versus mixed frequency model that get 369 citations. That was in 2011. There is another one in 2006 about leading indicators for US inflation with 208 citations. And I can keep going only with the papers published in the International Journal of Forecasting. So I just want to thank you for being one of our authors in the journal because you have contributed to the success. Okay, so I will stop here because now the important thing, as I said before, is to hear what Massimiliano has to tell us today. So, Massimiliano, the floor is yours. Thank you very much for being here.
Well, thanks a lot for this very nice introduction, and thanks a lot to John, Esther, and all the organizers for inviting me and for setting up this beautiful Congress. And they are so well prepared that, you know, they also prepared Italian weather for me with very hot, like I feel really at home now. Okay, And it's a particular pleasure also to give this Arnold Zellner Memorial. I mean, I don't have to tell you how good Arnold Zellner was, both for Bayesian econometrics in particular and also for forecasting. And so what I thought of doing is more or less to split the presentation into two parts. And the first part is just serving a little bit the kind of work that we did to try to accommodate all the kind of strange observations that unfortunately the pandemic period created in macroeconomic and financial time series. And then in the second part to go instead into the specifics of a paper, which is actually a Bayesian paper, again to commemorate Arnold Zellner, that goes a little bit more into the technicalities of what can we do. That is a Bayesian non-parametric paper. So again, the idea is that, as we know, the interest in forecasting and nowcasting and the value of what we do increases in particular when uncertainty goes up. And so when there are recessions during the pandemic period, with the Ukraine war and so on. And the problem is that, of course, forecasting in these uncommon periods becomes even more difficult. And so the risk is that we fail just when everyone is watching what we are doing. And we are in very good company because, you know, this is for academics, it's for those of you that work in the private sector, but it's also for those of you that work in public institutions. So if you look at the track record on forecasting of the Federal Reserve or the ECB or other central banks recently, it hasn't been so good. Okay. And so one issue is why is it so? So why we fail exactly when everyone is watching us. And I try to propose some reasons for this. Also, some of these are well known from the literature, but you know, one issue is that when we think of these extreme events like deep recessions or the pandemic, the financial crisis and so on, these are really kind of tail events if we think of the distribution of variables like growth, inflation, unemployment. And most of our econometric models instead focus on conditional means. So with our regression model, we try to model the expected value of y given a set of x's. And so in a sense, it's kind of natural that the regression models do not work so well when there are extreme events. And so one issue is what can we do about that? And the second related issue has to do with estimation. And so typically we estimate our econometric models using some kind of quadratic loss function. And so these quadratic loss functions are very sensitive when you have outliers. And so because of this, you can get very weird parameter estimates if you have just a couple of strange observations like the COVID observations in your sample and you don't do anything to treat them. And the third issue, related also a bit to the first two, is that at least the basic econometric models assume stable parameters and linear relationships between the target variable and variables that we use to predict it. But indeed, in particular, when we are in crisis time, we can get nonlinearities and parameter instability that we should somehow take into account. And the fourth reason that has attracted also a lot of attention recently is that typically, in particular in institutional models, we work with standard economic indicators, so the usual macro variables that you get from national accounts or similar sources. And these indicators are typically released with delay, and often they capture more the past than the present. And so also on the data, we should do something if we want to improve the performance of our models during crisis period. And so once we have identified a little bit the main sources of failure, we can try to look at possible remedies. And again, this is coming from some personal experience over the past now 2-3 years on how to handle these very particular pandemic period in macro and financial forecasting models. And so again, the first issue is, can we do something to go beyond modeling conditional means? And here, the kind of tool that is becoming used more and more often in macro is the use of quantile regressions. So on this, there is a literature that was popularized by Adrian and co-authors with this 2019 paper in the American Economic Review. And basically what they show is that when you look at the tails of the distribution rather than the center working with quantile regressions, you see, for example, that poor financial conditions can be associated with much deeper recessions than you know, the role of financial conditions during normal times. And you can find similar things for inflation if you look, for example, at oil prices or energy prices or unemployment and so on. And so here, the kind of work we did was to evaluate on the one hand whether you really need to go beyond the standard tools that we use, and second, to do instead more work on the specification of these quantile regression models for macro and financial forecasting. And so what we showed is that if you work with models with homoscedastic errors, like standard VAR or Bayesian VARs, indeed you have problems in matching the tail performance or behavior that you get from quantile regressions. But as long as you allow for heteroscedasticity via, for example, stochastic volatility, then instead often you can mimic pretty well the behavior of quantile regressions, because basically you can think of recessions, for example, as events where let's say the expected value of growth goes down, but also volatility increases. And this is what the quantile regressions are mostly capturing, but you can also do it with standard models with stochastic volatility. And then instead we did some work with Todd Clark, in particular Andrea Carriero, on constructing basically quantile nowcasting models. And of course there was a lot of interest since ever in finance on tail behavior, but again, not so much in macro. But if you want to monitor what's happening to the economy during crisis time, you really need to have this kind of continuous monitoring in the tails. And we have a new paper coming out now with that discusses all issues with classical and Bayesian specifications, because of course we are talking of very fragile models once you apply them to macro data, because if we work with 100 observations, say, and we look at the 5th% quantiles, you know, we have very few observations. That it's another problem in this. Second issue is instead related, as I was telling you, to estimation. And so what can we do to kind of robustify OLS type of estimation methods? Because again, they're very fragile when you have large outliers, because as you know, the method tries to somehow tilt the model parameters to fit the outliers more than the normal observations. And so this can bring to biased parameter estimates that then you plug into your forecasting models, and then this can introduce bias and reduce the forecasting performance of your model. So on this, thinking specifically of the COVID period, you may have seen a very nice paper by Shorefine and Song, who basically just suggests to completely ignore the COVID data. So you want to forecast 2022, for example, or 2023, you stop estimation in 2019, you freeze the parameter estimates, and you use these to forecast 2022 or 2023. So this is more or less as extreme as you can go, and they show that at least for the US, it gives you reasonable performance. So another way of doing this is, of course, to insert dummies. So the remedy that we learned as undergraduate, more or less. And we have a paper again with Carriero Clark and also with Elmar Menters at the Bundesbank, showing that as long as you are interested only in point forecasts, and indeed mimicking the results of Shorefine and Song, if you put one dummy for each month in the COVID period, the point forecasts do improve quite a lot with respect to a standard model without any dummies and with homoscedastic errors. The problem is if you are interested not only in point forecast, but also in interval and density forecast, so in conveying uncertainty, because that is very important, as we've also seen in the conference. And basically the point is that once you put dummies into your model, you are treating extreme events as known and deterministic. And so this leads you to interval and density forecasts that are too narrow. So you are by mistake too sure about your forecast. So what else could you do? There is a bunch of other things that have been suggested in the literature, for example, by David Henry and Mike Clements. One possibility is intercept corrections or other types of direct interventions on your forecast. And on this, we have a paper with Claudia Foroni and Dalibor Stevanovic, actually in the International Journal of Forecasting, doing something a little bit crazy, which is basically to ad hoc adjust the forecast for the COVID period by an amount similar to the errors that were made during the financial crisis. And this is a bit crazy because, of course, the sources of the crisis were completely different, the policy responses were different. But strangely enough, the method works pretty well, both for the US and for a set of other countries. Then you can do more sophisticated things than this. So these are, if you wish, first aid remedies. The other thing you can do is to move from the kind of simple averages that we do when we do OLS estimation and replace that with some kind of weighted averages of the observations. And so one possibility is to work with similarity-based estimation that is a little bit similar to the nearest neighborhood approach, where basically you overweight observations that come from similar crisis periods. And so this gives you parameter estimates that are kind of biased or tilted toward estimating specifically the periods that you are interested in. And again, in this period, in this paper with Foroni and Stevanovic, we show that this similarity base works reasonably well during COVID, but less well than intersect corrections. And the other thing that you can do is a little bit the opposite. So with similarity, you increase the importance of similar observations in recessionary or crisis periods. The other thing that instead you can do is basically downweight the outliers. So when you put a dummy, you give a weight of 0 to the outlying observations. While what you could do is, for example, switch from OLS to GLS, so to generalized least squares, allowing for heteroscedasticity. And so if you think about it, when you have a larger variance of the error, with your GLS estimation, you are just downweighting those observations that have larger variance and so that are more noisy and that have a louder signal about the parameter you are interested in estimating. And so for this, there are various ways of doing it. There is a nice paper by Lenz and Primiceri that basically work with a specific form of factor stochastic volatility for doing the downweighting, and they show that indeed this improves the forecast that you get from the model. And we kind of extend this again in this paper with Carriero, Clark, and Mertens, where we work with the stochastic volatility models where sometimes you can have jumps in volatility, because the problem of the standard volatility models during the COVID period are twofold. The first one is that it takes too long for them to learn. And so, the estimated volatility increases too slowly with respect to what was happening during the COVID period. And the second problem with the standard stochastic volatility models is that typically the volatility parameter is very persistent. And so you keep expecting and using very large volatility even when volatility is going down. And then again, this matters a lot, not so much for the point, but for the density and interval forecast that you get. And so with this outlier adjusted volatility, basically you allow for jumps both up and down in the volatility, and working with t-distributed errors rather than Gaussian errors, you also allow for a faster adjustment of your estimated volatility. And then again, this is then reflected not so much in better point forecasting, but in much better interval and density forecast. Okay, so that was about estimation. So how about instead the third big issue when you have crisis or other problematic events, which is the fact that typically the relationship between your target variable for forecasting and the predictors that you use change. So in this case, you know, there is a variety of parametric specifications nowadays to introduce time variation or nonlinearity. So think of all the classes of smooth transition, abrupt transition, Markov switching, change point models, and so on. And nowadays, the major improvement over, I would say, the last 10 years is that you can include this kind of extended modelization also in large and possibly very large models. So this is theoretically very nice. I mean, I like this stuff a lot. The problem is that when you look at the practical forecasting performance, at least ex ante, it's very difficult to pinpoint a specific model and a specific approach that is consistently giving you better forecasts for all variables and all crisis periods. And with Laurent Ferrara, who is actually here, and Matteo Mogliani, we did a pretty extensive evaluation, in this case focusing on the financial crisis, trying all of the models that you see in the first bullet points for many variables and many countries. And indeed, as you would expect, you find that for some variables and countries, this technique works. But you know, sometimes Markov switching is better, other time it's a threshold autoregression, other time maybe it's a model with stochastic volatility. So it's promising, but it's difficult, again, ex ante to think of this as a solution. And so this specification work, assuming specific types of parameter changes or nonlinear relationship. Another way is to go instead non-parametric. And so here, I mean, we did some work with George Capetanius and a variety of co-authors on basically various types of kernel estimation to allow for parameter time variation. And again, theoretically, this is very nice, but you know, one issue with this kernel-based estimation is that implicitly or explicitly, you need to assume that the evolution of the parameters is smooth over time. And instead, when we enter into crisis periods, so think about March 2020 with COVID spreading around the world, the effects can be much faster, and so the kind of jumps that you can experience can be difficult to capture with you know, just the standard kernel-based estimation. So this is about more or less estimation, but you will see something else that we are experimenting now, and the paper I will show you later on is trying to do the same non-parametrics, but in a Bayesian way. And so in a Bayesian way, again, also to honor Arnold Zellner's memory, you can work with priors to try to add additional information that would be more difficult to plug into classical kernel type estimation. So, and then again, fourth reason for failure of our standard forecasting models during crisis times is related, I think, to the kind of regressors, economic indicators that we use. So here we know, for example, that in normal times, parsimonious models with a careful selection of regressors are typically pretty good, you know, parsimony pays. On the other hand, the forecasting literature has shown that when there is crisis time, larger information sets can also be valuable. And so these emerged first with the work on factor models by Stocker-Watson on the one hand and Forney, Lippi, Allen, and Reichling on the other, and then with the literature on large and very large Bayesian VARs, both in single and in mixed frequency. And you can do even a little bit better than this by trying to target the information extraction from your very large data set. So, for example, I mean, I also did a lot of work on factor models estimated by principal components, but that is definitely not the best way of doing it, because with the principal components, you kind of summarize the information in your large data set without considering that you have a specific target variable in mind. And so you can refine these techniques, for example, the three-pass regression filter by Kelly and Pruitt, that it's a kind of extension of partial least squares. And in this case, your factor extraction will be specifically targeted to a prediction variable that you are interested in. And again, so these help. And so going beyond models with just 3 or 4 indicators and exploiting efficiently the information in large data sets is something that pays off. And again, a bit the issue is that typically we discover this thing ex post rather than ex ante. So after the financial crisis, we saw dozens of papers trying to pinpoint the specific financial indicators that would have been helpful. And now I've already seen, again, dozens of papers on the COVID experience thinking about which specific, say, Google-based indicators or other alternative indicators were useful during COVID and so on. So in principle, this is very useful, but we should try to do it ex ante rather than ex post. Now, of course, another branch of literature that has been used also to model the COVID period is related to machine learning. And in particular, if you want to use very large information sets to try to capture this kind of aspects that are missing from the normal models, you may end up with data sets that are so big that you really need to use some kind of machine learning methods. And we have seen some papers also at this nice conference. And of course, here there is a general level debate on whether machine learning methods are really suited for macro data, because, you know, typically the underlying assumption in machine learning is that there is a sparse data structure. So if you think of correlation matrices among these huge data sets, there are lots of zeros in those correlation matrices. While when you work with macro data, say 200 or 300 time series of macro data, typically the correlation matrix is all with values different from 0, and so there is a dense structure. And so the issue is whether the machine learning methods that have been designed for sparse data, typically IID data, can be also applied to dense macro data that in addition are serially correlated and possibly heteroscedastic. In the end, again, I guess there is a lot of space for theoretical work in here, but from a practical point of view, you know, there is no loss in trying them. And so, for example, Philippe Goulet-Coulomb, who's also at the conference, did a lot of work in this area, and we also have a couple of papers with him and other co-authors showing that, indeed, in particular, you know, to pick up the fast deterioration in economic conditions and then the fast recovery after policy was implemented, some machine learning methods, and in particular random forest, tend to work particularly well. Okay? And so then the kind of work that I'm doing in particular at the moment focuses with you know, something that is at the crossing of machine learning methods and Bayesian non-parametrics. And in particular, the kind of Bayesian version of random forest, or maybe better of boosted trees, is Bayesian additive regression trees. And this is the kind of paper that I will show you in the next 20 minutes or so. But again, there are other possibilities, like there are Bayesian versions of neural networks, and there are what are called Gaussian processes, where basically the idea is that you try to approximate nonlinear relationship across variables with infinite mixture distributions. And again, these are very interesting from the theoretical point of view, but at least from the kind of early work that we are doing, they seem to work particularly well when there are this kind of unexpected events, because they are models that tend to adjust much faster than standard regression-based models. Okay. And so that's a little bit the idea. And so before moving to this specific paper, let me just go back to something I briefly mentioned before, which is the use of alternative indicators. So to me, this is indeed very, very nice and interesting as a way forward to handle both specific periods, but also for normal prediction. I mean, we really need to use all the available information. And so Google Trends, you see web scrape data and the associated text-based indicators, mobility data, credit card transactions. So we did some work also for institutions, for Eurostat on this. I mean, one issue with this data, for example, but this would bring us far away from what I want to talk, is about data quality issues. So things about related to, you know, the open source availability of this data, reproducibility of the studies that work big data, how these data have been treated prior to using econometric analysis, how do you structure unstructured data like text analysis and so on. So again, this is something to be kept very well in mind, because it's something that can be very, very useful in general for prediction, and also in particular during crisis time. But again, it should be done maybe a little bit more careful than what has been done so far. And so after, again, this kind of broad and general introduction, mostly based on personal experience, let me tell you a little bit more about a specific paper that tries to put together a lot of the things that I told you. So large data sets, non-parametrics, machine learning methods, and specifically forecasting the tails, and so what happens in the percentile, highest and lowest percentiles, rather than in the center of the distribution. And again, this is based on a paper that we have just revised and came out as a working paper with Todd Clark, Florian Huber, Gary Koop, and Michael Farhofer. And again, the idea is that, as I was telling you, we are specifically interested here in modeling the tails of the predictive densities. And from a statistical point of view, this is very relevant and very interesting during crisis time, like the COVID pandemic, or what happened with for example, what happened to oil prices with the Ukraine war and things like this. And the problem is that you have to allow for a lot of non-standard features with respect to our standard regression models with Gaussian errors, because empirically what you see is that you get non-Gaussianity, you can get that these distributions have shapes that can change very fast over time, they have fat tails, and so on. And so we would need econometric methods that can generate all of these features that are empirically relevant, in particular during crisis time. And so on these, basically, Florian Huber and Gary Koop and co-authors started doing some work on the use of these Bayesian additive regression trees, or what we call BART. They have a paper coming out in the Journal of Econometrics showing that this kind of methods can indeed work pretty well for nowcasting. And so the idea of this paper instead is, do they work particularly well also in the tails rather than in the center of the distribution? And also, can we go beyond the standard BART models that were designed in the statistical literature to bring them more into econometrics and economics, and so use these to design various types of VAR type models, okay? And again, as you will see, we would like to use this approach both for modeling the conditional means, but possibly also to model the conditional variances, and so to go beyond the standard stochastic volatilities. And so these are basically non-parametric specification for conditional means and conditional variances. And then empirically, I don't know how much I will manage to tell you, but if you are interested, I put a lot of slides at the end with more results. So what we do is we apply these techniques to model these BART-based vector autoregressions, where we have 23 variables and 5 legs of each variable. So basically, these are very big regression models with like 115 explanatory variables, and they are handled non-parametrically. Okay, so just to show you that the thing can indeed be done. And part of the thing for being able to do this is that we managed to develop some pretty efficient MCMC estimation methods for these models that are scalable and that basically allow you to estimate the models equation by equation rather than as a system, okay? And then again, we will see how far we manage to go. So let me give you a little bit the idea of the model. So here, your basic model, oops, let's see if this works, is y depending on a set of variables x's, okay, in there, and the relationship is unknown. So it's a generic f function, and then you have your errors. And the errors also have possibly dependence, nonlinear and unknown dependence on a set on other covariates, explanatory variables z. So you could think of this, for example, as a very general, nonlinear generalization of a vector ARMA model. Okay? And so typically here in axis you put all of the legs, but you could also put other exogenous variables. And similarly in Z you could put, you know, either again the axis, or you could put legs of etas to get again the kind of moving average structure in there. And so the issue is we do not know F and G. And typically, F and G will be made up of functions that are equation specific. So think of modeling GDP growth, inflation, and an interest rate. The relationship between GDP growth and the legs could be different from the relationship between inflation and the legs. So you also want to allow for, you know, variable specific nonlinearities in here. And so the issue is how do we model these unknown F functions? And here is basically where this BART statistical literature kicks in, because what we will do is we will use basically averages of regression trees to approximate these unknown functions. Okay? So this is a little bit the idea. So here these H are actually trees, and moving a bit forward just to be sure. So this is how a tree would look like. So for example, this is something done for annualized GDP, I think for the euro area, in the end we did it. And so you see it's a kind of classification method, just for you that are not, those of you that are not so familiar with it. So here you want to arrive at modeling GDP growth. And you know, this is it's a tree because you see it has some kind of branches and it has some kind of leaves at the end of it. So this is telling you, look, if industrial production in the previous period was less than minus 16, move to the left branch. And then, you know, based on whether industrial production 2 periods before was lower or larger than minus 0.9, these would be your terminal nodes. Okay, and the number in parentheses tell you how many observations would fit into these terminal nodes. And similarly for the right branch here. Okay, so you see the right branch in this case is more elaborate. And so this is just a single tree. And this is what I'm basically calling H, okay? And so you see that this single tree is characterized by the branching structure. So how many branches would you allow? Is it a very tall tree with many branches, or is it a short tree with just a couple of branches? And by how many terminal leaves you want to allow for these, or terminal nodes as well. And then the idea is a little bit like when you do forecast combination. So rather than working with a single tree, let's try to work with many trees. So in this case, we allow for up to 250 trees and we average them, okay? And so this is a little bit the idea. So these trees are very efficient classification methods. And again, by combining many of them, as you would combine many, say, linear regression models to construct a pool forecast, you can get quite a lot of robustness and, in general, improvements in the forecast performance. And then again, the statistical literature basically shows you that also technically this is a good idea, because these trees are basically forming a basis that you can use to approximate arbitrarily well any kind of F function that you are interested in. And so this you can also do it again equation by equation, and you can also do it for G. So this is the main idea of this paper. So approximate these unknown functions with these trees, averages of trees. And okay, so this more or less I told you. And so of course there is a Bayesian way of doing this, but since this gets pretty technical, I'm going more or less to skip it. And instead, what I would like to show you is the kind of models that would fit into this framework, and those that we compare in the paper. So the first possibility, and the simplest one, is to assume that your F function is linear and there is no G. And so this basically returns you just a standard Bayesian VAR. So Bayesian VAR would be nested in this more general framework that you see in here. The other possibility is to have the standard BART model here. So in this case, there is no G. And so you just get that yt is equal to f plus epsilon, and then you use these averages of the trees to approximate f. And this is the model that was used in the Journal of Econometrics paper by Florian Huber and co-authors. So here again, we think of other possibilities. So you remember, for example, when you work with threshold models, but also in the machine learning literature, one idea is to add the complications to the linear model. And this is also how you would construct testing and blah, blah, blah. So in this case, basically, you could take your f function to be linear. And so this would give you the VAR. And then you use the BART approach to estimate G. So we call this mix BART because basically you are using the BART machinery to explain the nonlinear part of Y. So the part that is not explained by linear relationship between Y and X would be captured by your G function in there, okay? And again, this is also a little bit related with this idea of doing intercept corrections that I told you work pretty well empirically, because what you are doing is basically you are using in a very flexible ways legs of this eta t to try to improve the fit and the forecast from your model. Then we have something that instead we call error BART, and again, this is pretty similar to what we saw before, but with some little changes in the specification of G. And then we have the more general model that empirically will be one of the best performing one that we call full BART. And so this is the very general case where you have a nonlinearity in the relationship between Y and axis, and then you also allow for basically nonlinearities in the, if you wish, moving average part of your model. And then again, there are a couple of different ways of doing this that are discussed in the paper, but let me skip it. So the full BART is as general as it can get, and then you can get more specific representation going in there. So how about instead the conditional variances? So far, these were all models for the conditional mean. So for the conditional variances, we work with 3 specifications. So the main way we write it is like in the first line here. So this is basically a factor stochastic volatility model with the idea that this delta t is common to all of the variables. And again, this comes from the statistical literature. Mike West worked with this kind of models, and empirically we have worked with Carriero and Clark, showing you that indeed if you estimate stochastic volatilities for a lot of variables, typically you will find a lot of commonality in these stochastic volatilities, which also kind of makes sense. And then again, you have a kind of variable specific volatility part that is modeled like this. And so basically, you see that the overall variance covariance matrix of the errors has 2 parts, one that is common and one that is kind of variable specific. And so here, basically, within this machinery, you can set omega and h to fix, and this would give you the homoscedastic case, or you can use the standard stochastic volatility approach, or you can use, the BART approach that I was telling you before to also model specifically the evolution of the variances of the variable specific volatilities or of the common volatilities. And so this is what we call heteroscedastic BART. And again, you can think of this as a non-parametric way of modeling heteroscedasticity, if you wish. Okay? And again, this is based on work by Pratola and co-authors more in the statistical literature. So you just have to do this. Okay, so this, I think also due to time, we can also skip it. So this tells you a little bit how you would do this. And basically you need to set up a pretty efficient MCMC algorithm, as I was telling you before. And in particular, this factor stochastic volatility specification allows you to do equation by equation estimation. And so it allows you to break up the estimation problem that at that point you can do it variable by variable, so you can also parallelize it, and this makes it pretty fast. And the last bullet point here is just to give you an intuition of what you would do for the heteroscedastic BART volatility specification. So here the idea is a little bit like in stochastic volatility. So you square the errors and you take their logs, and then basically you model them with this kind of, again, weighted average of trees that in this case they are specific for modeling the volatilities, okay? Okay, let me skip this. So of course, this is a pretty non-standard thing. So the way you specify the priors on the trees and so on. But just to give you an idea, so here the priors are set in such a way that these trees that we use are very simple. So often they are trees with just 2 or 3 branches. But this, again, simplicity and then averaging empirically, we have shown that it works pretty well. And then if you have a chance to look at the paper, you will see that there is also a pretty extensive part on simulated data just to show you the performance of this kind of models. And in particular, to show you that at least in the simulated data, they work pretty well in the sense that if the generating mechanism is linear, they perform pretty similarly to the Bayesian VAR, while if the generating mechanism is nonlinear, they do much better than the linear VAR. Also at the means, but again, here we are specifically interested in the tails. So very briefly on the empirical application. So as I was telling you here, we work with a pretty large model with 23 variables and 5 legs. The forecast evaluation is done using fully real-time data and for a pretty long forecast horizon. For a pretty long evaluation period as well in here. And then for the evaluation, again, here we are thinking about the tails. So we need to find, let's say, the equivalent of the mean squared error when we look at the tails. And so for this, the standard measure is quantile scores. But the quantile scores, you look at the evaluation quantile by quantile, which is interesting by itself, and you find it in the paper. So for example, if you want to look at what happens in the 5% tail for growth or for inflation or an exchange rate, this is what you would do. Then you can try to put together all of these working with continuous rank probability scores, and you can also do some quantile weighted continuously ranked probability scores that look at the entire density but can give you different weights in the tails if you are interested in. And then there is something that is called energy scores, that is basically the multivariate version of the continuously ranked probability scores. That is something that you can use to do multivariate evaluations, okay? And so just since we do not have time, just a summary. Overall, this kind of BART-based models improve upon benchmarks. So in the slides, I put Bayesian VAR with stochastic volatility as a benchmark. If you look at the paper, there is also various versions of Bayesian quantile regression as benchmarks, or small-scale classical time-varying parameter models like those by Cogley, Sargent, and so on. And typically, working with this BART specification for the conditional mean gives you better tail forecasts. And this non-parametric specification for the volatility also improves a little bit with respect to stochastic volatility, but not so much. So why is it the case that this sophisticated heteroscedasticity modeling doesn't help you so much? Basically, because of the second bullet point here. So the point is that in this world, once you allow for this very flexible specification for the conditional mean, this soaks up a lot of heteroscedasticity. So the residuals of the standard BART model are pretty much homoscedastic. And so whatever you do to the errors and to their possibly changing volatility gives you some additional little gains, but really little gains. And so this is instead pretty different from the linear world, where adding stochastic volatility to a Bayesian VAR in general gives you a lot of benefits in interval and density forecasts, okay? So very final slide I wanted to show you, just to give you an idea of this machinery during the pandemic and also what can you do about it. So these are the density forecasts that come out from two of the models. One is a Bayesian VAR where there is a heteroscedastic BART for the volatility, and one is the full BART for the conditional mean with the heteroscedastic BART. So these are forecasts for the unemployment rate that you make 1 quarter ahead. So at the end of 2019 for the first quarter of 2020, and then at the end of the first quarter for the second quarter, and so on. So this is basically when COVID started to kick in. And so what I wanted to show you is first that this density is moving very fast. Okay, and in both kind of walls, and you know that even if you work with the Bayesian VAR, but you allow for this particular heteroscedasticity non-parametric version of it, you get predictive densities that are very, very different from Gaussian, that manage to capture this very particular, again, tail behavior that can be associated with extreme events. And then the other thing that you see in this figure is what you can do also with this machinery. So you can also construct scenario forecasts or conditional forecasts, which again is something that has been discussed interestingly in the conference. And the effects that, in this case, changes in the national financial condition in the United States have on the distribution, you see that they can change quite a lot over time. So during normal period, you see that financial condition indeed moved this distribution to the right, and in the case of full BART, they also made it kind of fat-tailed and possibly bimodal, while in the specific case of the COVID period, mostly thanks to the heavy interventions by central banks, financial conditions were not a problem at all, and so conditioning on different scenarios on this National Financial Condition Index has very, very little effect on the distribution, the predictive distribution of unemployment. And if you look at the paper, this experiment is redone during the financial crisis, and instead in that case you get a very different picture because this distribution were instead very, very sensitive to the level of the financial conditions that you got in the United States. And so also this kind of state dependence in the results that you get make this kind of model pretty attractive for modeling tail events like those associated with COVID. And I would stop here, so maybe we have some time for discussion. Thank you. Thanks.
Thanks a lot, Massimiliano, for this very nice presentation, full of references. So I just stress that at some point you say that there is currently a debate on the use of dense model versus sparse model, illustrated by this paper by Domenico Lenza and Premiceri. So I would like to maybe have your view on this, especially at some point you say that during crisis, recessions, it seems that it may be better to use a larger informational set than during expansion. So maybe if you could elaborate on this, that would be great.
Question. So indeed, from my experience, but also if you look at papers by Gary Koop on dynamic model averaging, right? Typically, when crisis kicks in, you need to average many more varied models, or the gains that you would get from factor models with respect to linear specification increase and so on. And I guess, again, one way of thinking about it is that since typically crises have different origins that are hard to pinpoint ex ante, by working with this larger information set or pooling more models like we are basically doing here, it protects you a little bit from not using the relevant information. And so if you work with just a linear regression model with, you know, think about an autoregressive model for inflation in the United States or other countries, that is as close, as good as you can get, right, in normal times. But when instead, like now, there are these you know, disruptions in the energy markets and so on, that model is no longer the best that you can do, and you need to kick in additional information. But in principle, you should do that ex ante. And so maybe one way to do this indeed ex ante is to work with this kind of models that are flexible enough to work with a very simple specification in normal times, but as soon as the model sees that things are changing, you see that it changes very, very fast the structure of the model that it uses. And I guess, again, this is a feature also more generally of this machine learning method. So they can learn very, very fast, faster than if we were using standard regression models. But very personal view, yes.
I like it, and a very impressive apparatus that you have developed. My question is, when you generate these graphs over a short period of time, looks reasonable, but it could be just part of our imagination. I mean, is it correct? There is no way of checking against reality, right? This is just part of our imagination, isn't it?
Yeah.
Can you check? There's no fact that these are correct.
No, that's casually, it's another very good point. So, I mean, you can do some kind of ex post evaluation. So basically looking, I should get maybe some pictures later on. So for example, this is how, you know, the quantiles of the predictive distribution would be evolving over time. And here you have, in particular in the top one, the evolution, this is for inflation. And so you get the various quantiles from at different levels from the different distributions. And in a sense, you see that more or less the actual GDP, in this case inflation, is indeed in between. And this is how it works during COVID. So COVID requires a very different scale, so that is why it's put aside. And so you see that, for example, here it didn't do a good job at the beginning, but then somehow it kicked in again. So this just to give you an idea. So in the paper there is more about it. So the idea is that again you can do an evaluation of this kind of tools more or less. For example, quantile scores tells you that say you know, if your model predicts a certain number of times that there will be a tail event, then you can match that with the realized values of the data and see whether it has correctly predicted or it has over-predicted the occurrence of tail events and so on. So there is a part of ex post evaluation that you can do also for this kind of tail forecast. Of course, again, my problem with this is that we are working with very, very few data, very few data points. And so if you were to put uncertainty on the uncertainty, this thing would be huge. And so in the quantile literature, there is a literature on extreme quantiles like Viktor Chernotzokov and this kind of people, but we experimented also with that, and at least with macro data, it doesn't seem really to help you that much, but it's very relevant.
First, a comment on the issue of getting higher frequency, more timely data. This seems to be very, very important. And it's not only important in the modeling and forecasting context, but also in the policy context. And we know from the financial crisis that there were massive revisions to the data for 2008, such as GDP growth. And having only the preliminary data created a lot of confusion, if you wish, in policy circles, because we thought GDP was growing. In fact, it was actually falling. It became even more critical coming to the COVID pandemic, where things were changing not on a month-by-month basis, but on a week-by-week or day-by-day basis. And there's a really fascinating account that Rich Clarida, Chiara Scotti, and Bursu have written on what the Fed was doing at the time. So that, you know, and it was very much focusing on a lot of the high frequency data. So I'm very sympathetic with that. There's an important caveat in that the relationships often seem transient. And we know that from the work on Google flu data, that it worked brilliantly until it fell apart. So that is something to be analyzed in this context. It would really be interesting to see the results on that. The second concerns this issue of tails versus shifts in mean. And perhaps for financial data, you might think of it as being a single black swan or a couple of black swans right at the beginning of the pandemic. But if you look at labor force participation rates, 2.5 years of black swans does not seem like an outlier or a tail event, but actually a shift in the mean. So for these sorts of intercept corrections, you may need to have designer-specific intercept corrections, some of them shifting permanently, others tapering off, other being very short-term. And so it'd be very interesting to look at that in the same context that modeling breaks is gone.
Oh, thank you. These are very relevant issues. So starting with the last, indeed, I mean, I was a bit skeptical about this machinery because, you know, I am a simple guy, so this looked a bit too complex. But actually, this is doing exactly what you have in mind, because this, when there is, for example, a mean shift, this machinery adds a couple more trees to capture that, and it gives them larger weight. And when the situation goes back to normal, it's pretty fast in lowering the weights of these trees that it has introduced and bringing you back to normal. It's a kind of unsupervised learning that seems to work pretty well. Again, if you, my point is that you should always use all the information. So for example, if you know that there has been a permanent shift in the participation rate, it's much better to impose that in the model than go unsupervised like this. But for sure, that is very relevant. And very true also about the real-time data and the thing. I mean, we are still in a very weird world. So you may have seen that, like, well, first quarter GDP in the United States was negative and unemployment is at 3%. So it's really a different world. And now the nowcasting model of the Atlanta Fed predicts -1, -1.5 for the second quarter. So technically, there would be a recession in the United States, but I don't think the NBR would call this a recession with the level of unemployment that we are seeing, even though, again, participation rate dropped a lot. So it's really uncertain times. It's really, but in a sense, it's also, as we know, from this kind of variation that we learn more about underlying relationships in economics. So let's hope that COVID goes away, but maybe we still can learn a little bit from what has happened to reduce a bit the losses that we got. Thank you. Yes. Thank you. Thank you. Thanks a lot. Thank you.